numbers, right? If the transformation takes the order is lower than n log n, and then if the solution for Voronoi diagram is lower than n log n, what does that tell you? It tells you that you can solve the sorting n numbers, with the complexity lower than n log n, right? Because the transformation take as an order lower than n log n, right? And if this the solution for Voronoi diagram, the complexity is lower than n log n, then the order to solve the sorting n number will be lower than n log n, right? But we know it's theoretically impossible, right? It's theoretically impossible, which means what? Because the transformation can be constructed. So the transformation there's no issue with the transformation. But the issue is you assume there's a quick way to solve the Voronoi diagram problem. So Voronoi diagram solution has to be at least n log n, right? In order to to say like, okay, even if you call the Voronoi diagram to solve the sorting problem, the complexity wouldn't be lower than n log n, right? Right. So this is like the way to do problem reduction. Okay. I mean, I didn't really discuss how do we transform the sorting problem into the Voronoi diagram. Okay, but to be honest, okay, that type of problem transformation is not part of this class because it is part of the algorithm class. Okay, if you take the algorithm, it should tell you the NP-complete problems, and the NP-complete problem, the whole NP-complete problem concept are based on the problem reduction. Okay, so I think I will refrain from, as I said, like there are different classes will cover different things. So I will not cover that. I will just tell you the basic concept, but the real examples, I hope you can learn that from the algorithm class. Okay, we have some very good instructor in our department to teach. Yes.
Remember the omega notation means lower part.
Yeah.
Does that mean the Fortin's algorithm might require more than n log n?
Actually, it's n log n. It is n log n.
Why not you just write big O?
Big O is upper bound. Yeah. I mean, don't worry about this. I will just tell you it's n log n. Okay. I mean, take my word. Okay. I mean, for that. Okay. So okay. Hopefully you understand the idea of problem reduction. But here, okay, really, I mean, what I want to tell you is that okay, we could prove that Voronoi diagram take at least n log n to solve it. And of course, if you want to start it like this problem reduction for Voronoi diagram, I mean, there are references. You can check it out at the end of this chapter. Okay. So we are the algorithm, the Fortune algorithm that we are going to discuss is a variation of plane sweep. Okay. Why do I say it's a variation? Because yes, we do have remember plane sweep. I mean, we have a horizontal line that is like keep going down. Okay, at every event point, right? Okay, so in some sense, yes, we still have that horizontal line. I mean, going down. Okay, this part is the same, but in the original plane sweep algorithm, the stuff that we considered, okay, will be normally will be everything above the sweep line, right? Will be everything above sweep line. I mean, to be honest, normally will be right above sweep line. What happened right before this? I mean above the sweep line, or at the sweep line, whatever you want to call it. But here is different. Here is different. Okay. We call that consideration as a beach line. Okay, beach line. Okay, so it looks like this. Okay, we have this is our strip line, and this is the beach line. So, what is this beach line? Okay. Beach line is the boundary of the Borel diagram that will not change after strip line move down. So basically, okay, at this moment, okay, everything above on top of the beach line will not change. They will not be affected anymore. But in between beach line and the strip line, as well as the stuff below the beach line, of course, they may still change. They may still change. Okay, so this is why we call this as a variation. It's a variant of plane sweep algorithm. Okay, even though we talk about plane sweep algorithm, how many times? At least twice, right? Twice. Like we talk about plane sweep algorithm to compute like the intersections of some line segments, right? And we use plane sweep algorithm to talk about the triangulations, right? Triangulations. Remember arc gallery. We use plane sweep algorithm too, right? After obtaining the Y monotone pieces, we need to cut it into some triangles, and that is we use a plane sweep algorithm there too. So I hope by now you have a very clear idea of what a plane sweep algorithm is. That basically you have a data structure to maintain what we call event points that basically control like how this what should I say, like this horizontal line, how this horizontal line moves down, okay, because like it actually moves down only at the event side, right? Only at the event side. And on the top, you also have another data structure to maintain this beach line. Okay? So how do we do this? Okay, so that's, we probably need to get more understanding of this beach line. Okay, because I just show you, those are this wavy lines are beach line, but what are those like curves? What is the property of these curves? So I need to discuss and to tell you. Okay. So the part of the Borel diagram above that cannot be changed anymore. If point Q, okay, is in this L plus means like this is L, this is our straight line. Okay, L plus means the stuff like below it. Okay, so we want to make sure the side, okay, after this line, okay, behind this line, if there's a side behind this line, they will not change. It will not change your model that would above certain location, then what is the property of this fish line? Okay. So, okay. So if the point Q, okay, to any side below, oh sorry, L plus. Let me correct myself. L plus is the top. L minus is below, the half gap below. L plus is the top. Okay. So when you find that Q, okay, on the top of this strip line, okay, that will not change, okay, that will not be affected, okay, by any side below, okay, because obviously it's greater than the distance of Q to L itself, okay. Otherwise, I mean, then it will not change, right? Because if you have any side behind L, then the distance to that side will be greater than the distance to the L, right? So if you try to draw it, okay, for example, consider this point. Consider this point. That means what? The point to the distance to this side and the distance to this side, to this line should be the same. So what is the geometry element that has such a property? Let me repeat. The distance to a point will be the same to the distance to a line. Hey, look at the shape. Does that tell you something? No? No? No. Okay, when you talk about that creates eclipse. Okay, eclipse basically has two important points. Okay, so it's not eclipse. Okay, it's what? It's parabola. You don't know what parabola is? 抛物线. Okay. You need to understand, like for example, in high school, you learn different type of geometry objects, such as parabola, such as, well, I think parabola, you probably learned that from junior high. I'm not sure, right? But in junior high, probably you just know the formula. You don't. I mean, you probably didn't discuss like the property of parabola that deep. Okay, but in high school, okay, you should know. For example, okay, for parabola, okay, parabola is formed by the point such that for a given point, for a given fixed point, a given fixed line, okay, the distance to that fixed point and distance to that line, okay, I mean you have equal distance, then you can draw a parabola. Okay, so this is for parabola. This is very important, and that point, okay, for the parabola actually it has a name. It's called locus. 焦点. Okay, and by the way, the physical property. This has nothing to do with this chapter. Okay, by the way, I just want you guys to know more about geometry. Okay, I kind of feel sorry for your high school teacher. Yeah. Anyway, okay. So for example, like this is very important. Actually, also in your high school physics. Okay. To be honest, like our department actually canceled the physics class. Like but when I was like the vice chair for the department, 主会是 Zhang Jiahui, okay, she was a chair at that time. She and I went to the physics department to get the physics class canceled. That's because of our department's idea to cancel this class. But to be honest with me, to be with you, I'm not voting for canceling physics class because I think physics class is actually very important. Okay, so for example, if this is locus for your parabola, this is a line. Okay, line for this is given line, given point. So this is a locus. This is line, and then if you try to draw any line, okay, and the refraction will all be parallel. Okay, you should learn this from physics, the light, 光学. Okay, where he talks about light, the property of light. Okay, so this is very important. So how about the other geometry shape? I mean, you know circle. I mean, you learn that from junior high. I mean, come on, you know, I probably shouldn't talk about circle, the property of circle. It's too obvious. How about the eclipse? I mean, you guys, one student just mentioned eclipse, right? Eclipse, okay, it's formed by there are two points. We also call those 2 points locus. But the eclipse is formed by given 2 fixed points. Then the sum of distance to these 2 points is constant. So for example, this distance plus this distance will be the same as this one plus this one. Okay, that is the property of eclipse. Okay, so you need to understand this geometry property. Remember, this class is called computational geometry. So when we make use, when we try to design a solution, we need to understand the geometry property. So this fundamental geometry property objects, their properties are very important in this class. Okay. Anyway, I mean, of course, this has nothing to do with this chapter. Okay. The only thing that is important is okay, given a fixed point and a fixed line. Okay. The points that have the same distance to that given point and the given line will form a parabola. And that point, that given point is locus. Okay, so actually, okay, these pitch lines are composed of a number of parabola. Okay? And we know that this pitch line is X monotone. What is X monotone? Remember we talked about Y monotone pieces, right? What is Y monotone pieces? Remember? Like if you try to have any line perpendicular to your y-axis, it will only, intersect with that piece for a continuous portion, right? Okay, so the idea is similar. Okay, so we say this pitch line is X monotone. That means that what? That means, okay, if we draw a line that is perpendicular to X coordinate, X axis, which obviously will be the vertical line, right? Okay, if you draw a line that's perpendicular to X axis, it will be vertical line, right? So the vertical line okay, whichever vertical line you draw, you will intersect this pitch line in exactly only one point. This it should be very easy to see because think about this. We have a number of so each of them is part of the parabola. I mean, can you have something that is then you have 2 points. This is not pitch line, right? Right? I mean, this obviously this parabola will be gone, right? Will be covered by this parabola anyway, right? So it's impossible to have like a vertical line that intersects this pitch line by 2 points, right? Okay. So far so good, right? Okay. And because of that, you know you can sort of like store these pitch lines, you know, in a left to right order, because as I said, like there's no pitch line no multiple pitch line like lying at the same x coordinate. So you can sort of like you know, represent those pitch lines by a number of parabola from left to right. Okay, from left to right. So, but we still need to discuss how, even though previously I was talking about like, okay, this is like the pitch line are formed by parabola, but because when you move the line, at the same time, this parabola will change, right? The parabola will change because, well, remember, it's equal distance to a point and that line, right? But when you move the line downwards, of course, the corresponding parabolas will all change, right? I want you guys to be aware of that, okay? So where a new arc may appear on a pitch line, it is when we call that thing as a side event. It's when a side, I mean this line actually encounters a side. When a side is encountered by this straight line, okay, that point, okay, think about this, okay, that point, okay, is a special case, okay, I mean, you will have a degenerate case, kind of like, you have a pitch line here, but at this point, okay, you have a straight line going down. Why is that? Because, what should I say, the distance to the point, the distance to the distance to the side, the distance to the point will be the same. Well, then it's going to be this point, right? And every point here will have the same point, same distance to the side and the point, right? So this is special case. But when you go down, it's going to expand. It's going to expand. It will be something like this. When this vertical line, horizontal line moves down a little bit, you will see this pitch line. This pitch line actually will be cut. You can see this part and this part actually comes from the same parabola, right? But you are going to have a new parabola that's sort of like a break original parabola into two pieces. Okay, so this is like what we call side event. Side event, when your straight line encounters a side. Okay, so far so good, right? Okay. So I tell you that this is how a new arc appears on the pitch line. But you may ask, is there any other possible cases that an arc could appear? Okay, is there any possible cases an arc could appear, like not by a side event, but by something else? Okay, because a side event sort of cover the situation that the new side, like we encounter a new side, so the arc actually was created because of the something arrive at this 3 pi, right? So we are asking if there's a other situation that not necessarily because of the side appearing down below the beach line, but it may be because we'll move down the beach the strip line. Okay, maybe because of some because these are some parabolas, right? Maybe some parabola will go down. Some parabola will go down and break the other parabola. Okay, so this obviously is not caused by the new side arrival, right? So is it possible? Think about this. Okay, if this happened, okay, say if an arc, going down to break the beach line, okay, because of the strip line moved down, okay, there are 2 possible cases. The first possible case is that this beach line, this parabola, okay, actually break a certain parabola that is already part of the beach line, okay, somewhere in the middle, which is kind of like this case. This is the first case. The second case is that, okay, for similar situation, like this parabola will go down to break our beach line, but it will break the beach line at this point. This point is happen to be an intersection, a joint of 2 parabola. Okay. For the first case, it will be a point, a particular point that, okay, you will see this is beach line, okay, and you will see this beach line for particular time, given time. There will be a situation. These two parabolas are tangent to each other, right? Okay, are tangent to each other, and because these two parabola, of course, they are based on different sides, right? They are based on different sides. And think about this. This L is the same, right? This L is the same. This L is the same. But one side may be here. The other side may be another one. Okay, next you try to make this one P1, maybe this one P2. And then you try to create the formula for these 2 parabola. It should be too difficult, right? Assuming you're high school, you didn't flunk your high school math. Okay, then it should be easy. For a given point, for a given line, okay, come up with the formula for the parabola. Okay, then you will find that you try to because okay, geometrically, when these 2 when these 2 parabola are tangent to each other, that actually means that when you put these 2 formulas together, you should get only one solution, right? Only one solution, right? One xy right? I mean, I hope like you know like the relationship between the geometry and the formulas, right? Okay, when they are tangent, that means that these two equations should give you exactly only one solution. But if you try to represent those things in equation, okay, which obviously may take some time. I mean, it shouldn't be too difficult to you will find that it's impossible. Okay, for two parabola to be tangent at one point, it's impossible. You will get either 0 solution or more than 2 solutions. Okay, it's always the case. Okay, so this is not possible. This situation that two parabola are tangent at a certain point, it's not possible. Okay? So the other case, as I said, is that this parabola, when you move down this straight line, it breaks the joint of two parabolas. Okay, this is the second case. Remember, keep in mind this second case when you do like when you join these form equations to solve it. I mean, look at this equation and this equation. I mean, they are joined at the 2 points. Yes, they are joined at 2 points. Or this equation and the other this equation, they are also joined at two points. That's fine. So you cannot use like equation solving to prove that this is not possible. But okay, again, when there will be a situation again, this parabola will actually happen to have to be like to go through this joint. Okay, so let's assume. Okay, the side for the left parabola to be pi, the side for the right parabola to be pk, and the side for this upper parabola, okay, to be pj. Okay, when parabola happen to join at one point. Okay, physically, what does that mean? Remember, it means like okay, the distance from pi to this line to this joint, we call that the joint as q. Okay, okay, the distance from q to pi and from pi to this L, the distance should be the same, right? Okay, that's because of this parabola. And for the same reason, the distance from pi to q, the q to pk and the pk to L will be the same, right? And also for the same reason, distance to pj to q and the q to this line will be the same, right? So because of this, when you draw a circle, the largest circle without containing any side inside, this q is just joint. Okay, it's not a side. Okay, it's just a joint of some parabolas. It's not a real side. Okay, so this largest circle using q as a center will have pi, pj, and pk at the boundary, right? Also, you could imagine this L, this circle will also be tangent to this L, right? Is it good so far? Okay, so because of that, remember what I told you earlier. Okay, when you have a largest circle, okay, will go through 3 sides. without any side inside it, that point is what? It's a vertex of your Voronoi diagram, right? It's a vertex of your Voronoi diagram. Okay, so that Q actually represents vertex in your Voronoi diagram, if that's the case. And then, if you try to, if that's the case, then that point should have should induce some edge, right? It should induce some edge. So when you move this line L a little bit, just very, very small, a very small distance. Imagine when you move this L down, just a very, very small distance, like here. Okay, well, here we draw it a little bit large, big. We move a little bit large, further. But you imagine this distance is very, very small. Okay, and what happens is that you can imagine. Okay, if you want to draw a circle, okay, that is tangent to L, and which goes through Pi and Pj, then you must include Pk inside it, right? Right? You must include Pk inside it, right? And then on the other hand, if you want to have a circle that is tangent to L, and which goes through Pj and Pk, then the Pi will be inside the circle, right? Right? What does that mean? It means that, okay, if from here we know this is the vertex, right? That vertex, as I said, it should induce some edges, right? It should induce some edges. But remember, in the previous discussion, where is it? Here, the second one. Well, if there's an edge, okay, if there's an edge, then the larger circle that goes through two sides shouldn't have the third side inside it, right? So it doesn't matter. It doesn't matter. How you draw it. If you go through Pi and Pj, well, in this situation, you include Pk in this line, in this circle, inside the circle, which means what? Which means, well, then you shouldn't have any edge that is coming out of Q. Okay, or the other way, if you want to do like the same thing for Pj, Pk, you will include Pi in the center. So you shouldn't induce any edge from Q for the other direction either. So well, it's a vertex, but it doesn't induce any edge. That's impossible. Hmm?
That doesn't mean the induced edge is not containing the center of the circle you draw.
The induced edge is not containing the center. No.
It obviously induced three edges.
You induce three edges. Yeah, it will induce multiple edges, right? Yes. Then what's your question?